predicates. A language is essentially a collection of predicates. So we can have predicates over state, things like something is true in all states or in some states. Almost all states is a useful one to have. That's the door example. It is almost always closed. And we can give a precise definition to that. For non-deterministic state, we have things like definitely and possibly. Definitely true if it's true for all values of that non-deterministic state. Possibly true is that it may be true for some of them, but not all values. And I'm going to use that in a little example in a moment. Next. So, I don't know, mind pump case example. How many people have heard of the mind pump example? A few people, so it's often used.
I think that you can.
It's a very simple thing. It's a mine, as in a coal mine, underground, obviously. And there's two threats in a mining situation. One is to flood, because it fills with water, and the other is explosion, because it fills with methane. To get rid of the water, you pump it out. But the pump can produce sparks. So when the methane is high, you want to not run the pump, because you could get an explosion. Because flooding is bad news, but explosions are really bad news in a hierarchy of bad news. So the mind pump example has monitoring of the environment, monitoring methane and carbon monoxide and airflow, and looking at the level of water in the sump and control over a pump. And there are different times. We'll be able to use this example because the interaction with water is at a much slower time span than the interaction with the methane. Water at minutes level, methane at seconds level. So you pump water if it's high but not while the methane is high. And so we can get statements like, if it's possible that at any particular time band, if it's possible for the methane to be above the critical level, then it's definitely the case that the pump is off. That's the requirement there. So if we had also, if we now start to talk about a controller, if we put the controller, say, at the minute band with a precision of 5 seconds, then we can make these statements. If it's possible for the methane to be greater than some critical value, if that's possible, then it's definitely the case that it's above critical value less this value here, which is the accuracy of the methane reading. So this is how much the methane can change during an event. You take that away from critical, and then that is definitely true. So I think I just draw that. If there's some level which is critical, it's the critical level for methane, I'm going to put a value down here which is C minus the accuracy. So at any point, methane is above critical. If it's possibly, in any value that you could have had, it's with above critical, then all of those values are going to be definitely above this one. Now this one you can observe because it's definitely true, whereas this one you can't necessarily observe because it's only possibly true. So it gives us a way of talking about the controller. And so the specification of behaviour is the methane now, not critical, but we define some threshold and say, I want this immediate behaviour. If the methane is ever observed to be above the threshold, I want to turn the pump off. That's an immediate statement.
You may have posed a question to the previous one somehow. Because you only state that it's possible that the methane is critical, above critical. Not definitely.
No, it's not. Yeah, because what you're concerned with the above behaviour here, because you're saying critical. So if it's at all possible that the methane is above critical, you definitely want the pump to be off. But you can't observe the environment perfectly and instantaneously to know whether the methane is or is not above critical. You know, you could get methane level going up, down, below, down, below, down, below. And you observe here, here, and here, and it's never above. That's certainly possible, but you don't want that to be true. So you move away from this observation to something that is definite. So we have as a controller, if the methane is higher than some threshold value, we want to turn the pump off, and then you can deduce merely from the parameters of the time-bound model what that threshold value has to be. It's got to be less than critical. You get this relationship to do with the rate of change of the methane and the accuracy of the methane at the minute level and at the second level. Won't go into detail of that, but you can construct the constraint on the threshold value in order to give yourself safe control. The point being, stepping back to the details, the point being, I can specify my requirements in time bounds, putting them in particular time bounds, and never have to mention time. I say, I want this to be immediately true. Methane's high, pump off. And I can specify those without mentioning time, because one of my starting points for this work is that people do not talk about time very sensibly in requirements. So here I'm giving them a framework which says, well, if you put that specification into a particular time bound, that's where it inherits the semantic information about time from the time bound that you put it in. So my half an hour talk is slightly running over. So just to conclude, complete complex systems exhibit behaviour at many different timescales. And rather than base hierarchies on structure and then look at its timing properties, I'm arguing here that you should initially construct a hierarchy based on the dynamics, based on time, and then add structure to that. Remember the notion of time is not the same in all the time bounds. It has been with the sort of technical examples with seconds, milliseconds, etc. But once you start talking about human behaviour, and organisational behaviour, and social behaviour, then there are other notions to do with time that you want to bring into the system description. And we're also interested in being able to predict how you get emergent behaviours in systems, essentially by projecting up from phenomena that might be reasonably random on one time bound, projecting that up to a higher time bound and potentially observing emergent behaviour. You can, and hardware people do that, you can have asynchronous circuits at one level and have a fairly synchronous time behaviour at a higher level built from asynchronous circuits. And that's an example of an emergent synchronous behaviour from an asynchronous behaviour with certain constraints on the stochastic nature of the random behaviour at that level. So emergent behaviours, being able to express emergent behaviours is one of the things we want to do with this. And we've also played around with the argument that in the work on cyber-physical systems, and I'm sure because Eduardo's here, is something you all know about. Again, I think that the time bands is a useful way, an introduction of one of the formalisms that might be useful in cyber-physical systems, because you are talking about continuous and discrete, you are talking about technical communications and the broader environment in which an embedded cyber-physical system will sit. So if you want to plot them, I'll take obviously questions, whatever, but if you want a technical question to think about, here I've got two time bands, I've got two events, E1 and E2, with a precedence relationship. They map to activities. What's the relationship you should have between those activities in order to be consistent with the notion of precedence of the higher time band? It's actually something to think about. But that was all I was going to present today. Thank you for listening in both rooms.